Hi everyone, in this lesson we're going to cover section 1.3, which is all about collision theory. There are 4 goals in this section of the chapter, so we're going to talk about rate laws today and explain what a rate law means. We're going to describe 2 things that, according to collision theory, will affect the rate of chemical reactions. We'll describe the requirements for effective collisions, and finally we're going to define activation energy, which is going to be used in our potential energy diagrams that we're going to study in section 1.4. So before we even get started with collision theory, I have left your TOC with an introduction to collision theory from the crash course video. So I'll give you some time to do that, and then you can come back to this video. After the video, you should have a brief understanding, a preliminary understanding of what collision theory is and what sort of things will affect our chemical reactions. So we're going to try this warm-up activity together. If you would like to work on this warm-up activity in your workbook, it's on page 24, at least in my version of the workbook. Otherwise, you can do it straight on the piece of paper that I've given you. But we're going to consider this kind of hypothetical reaction. So we're going to think about gas particles. We've got A and B that are reacting to form AB. So if we're going to let the squares equal A and the dots equal B, what we're going to do is just track the total possible collisions. So in this first example, A could hit B, and that's the only way they could form a collision, so we have 1 possible collision. With this one, we have 2 of A and 1 of B, and so either this particle could hit B or this particle could hit B, so we have 2 possible collisions. With the third scenario, we have 3 A's and 2 B's. So if you can see the arrows that have been drawn in there for you, this B down here could hit either A1, A2, or A3, and this B2 down here could hit A1, A2, A3. So there's a total possible collisions of 6. And hopefully you've kind of gotten the point of what we've been doing here. We've got 1 and 1, so 1 times 1 equals 1. 2 times 1 gives us our 2. 3 times 2 gives us 6 possible collisions. So with this one, we don't even need to go ahead and draw the arrows here. I've got 4 A's, 3 B's, 4 times 3 is 12. So I've got 12 possible collisions there. So when we're looking at the relationship between the number of A and B particles and the total number of distinct collisions, our possible collisions is multiplying those 2 together. So possible collisions is equal to A times B. So it's dependent on A, the concentration of A, and the concentration of B. When we're talking about a chemical reaction, we know that not every time particles hit together, not every time do they actually form a successful collision, but we can say that the rate is proportional to the number of collisions. So we use the Greek letter alpha to represent proportional to. And the rate is proportional to A times B. And there's a number of different factors that are going to affect how fast that rate actually is. Number 1 being temperature. So from this, we can go into a generalized rate law. When we have a reaction rate, our reaction rate is equal to, now you'll notice that this time I'm using is equal to instead of proportional to, and I'm going to put in K to represent a rate constant, the concentration of A to the X power times the concentration of B to the Y power. So we're just going to define all of these different terms in our rate law right now. K represents a rate constant. And the rate constant is going to depend on the species that are involved. So it's going to depend on what kind of chemical A is and what kind of chemical B is. It's also going to depend on the temperature of the reaction. So that rate constant is very specific to the type of reaction. When we use those square brackets, it represents a concentration. So this is our concentration of reactants. And we've got the two reactants. We've got reactant A and reactant B. And then finally, this X and Y are experimentally determined. These are called our reactant orders. And we can't predict the reactant orders just from looking at the equation or looking at the chemical formulae. They are experimentally determined. So that is the general rate law. Now, one thing about what we're going to be studying, we are only going to be focusing right now on reactant order of 1. So we are going to be spending the rest of today's course looking where X is equal to 1 and Y is equal to 1. But it's just nice to know that there are higher orders that are possible, and the concentration will affect these more because suddenly it's to a second or third degree power. So I'm just going to summarize that. We focus on reactant order 1. So X is equal to 1 and Y is equal to 1. But higher orders are possible. If we do have a higher order, we know that concentration will affect these more. So the next thing that we're going to do is we're going to do a quick check. This is on page 25 of your workbook if you want to do this in the workbook. Otherwise, you can follow on paper. It's just a quick check to kind of go through and make sure that everybody is on the same track. We know what's happening. We can understand the math behind this as well. So you can kind of pause this video at this time. Give yourself 3 or 4 minutes to do the quick check. Try the answers on your own, and then we'll go through them as a class. Okay, coming back, the first quick check question, says, write the general form for rate law with two reactants, C and D, when they react together. We are assuming that we have a first order for each reactant. So what we're going to do here is we're going to take our general rate law. Our rate is equal to the concentration of my reactants. So I've got C and I've got D. When I do a generalized rate law, we also have to have a constant. So I'm going to show the constant as a K right out front. And then because we're assuming that this is a first order for each reactant, we can assume that each of these is to the first power. So I could put the 1 in here, or you can just leave it blank. It's totally up to you. So in this particular rate law, what the rate law means is that the reaction rate is proportional to the concentration of reactants. So I'm just going to use that alpha to represent proportional to the concentration of reactants. Now, with quick check question number 2, it says assume a reaction occurs by this rate law. So we have a constant times the concentration of A. How would the rate be affected by each of the following changes in concentration? If we are doubling the concentration of A, anything we do to the one side, we also have to do to the other side. So if we're doubling this, we're taking A times 2. That means that the rate is also going to be times 2. So we're going to be doubling the rate. Likewise, if we're halving A, we're going to be dividing A by 2. We're going to take the rate and divide it by 2, so we're going to have half the rate. Okay, with question number 3, we have a little bit of a tricky situation here. It says, assume a gaseous reaction occurs by this rate law. We've got rate equal to K times the concentration of A times the concentration of B. How would the rate be affected if the volume of this container were halved? For this question, we have to do a little bit of thinking. What happens to the particles when we take that container and we half the volume? So I'm going to pretend here is my original container. Here's my particles. Let's say I have A's and I've got B's. What I'm doing now when I half that volume is I'm smushing the A's. The A's are still all in there, but now they're more concentrated. So effectively what I've done is I've doubled the concentration of A, and I've doubled the concentration of B. Now if we look at that with our rate law, we're going to take A times 2, and we're going to take B times 2. Anything we do to the one side of the equation, we also have to do to the other. So I'm going to take my rate times 2, which is equal to 4 times the rate. So I'm going to say the rate is quadrupled. And finally, the last question here, how is the rate of the reaction affected by increasing the temperature? So if we are increasing the temperature, we know that that's going to increase the velocity of the particles. So we're going to increase velocity of particles. This is going to lead to more collisions. And if we listen to the notes from yesterday, if we really took those in, it's also going to lead to more effective collisions. So my reaction rate is going to increase. Now we have to figure out what part of the rate law must be affected by changing temperature. Because increasing the temperature is not going to affect the concentration of C, it's not going to affect the concentration of D, it's not affecting the concentration of those reactants. The thing that must be affected is the constant. So K is affected by changing the temperature. So that gave us just a little quick check, make sure that we know what we're learning and can apply it as well. So we're going to go on now to collision theory. So we've talked about the effectiveness of the collision and the number of collisions per unit time. This isn't really new, it's just putting it into new words. So when we talk about collision theory, the reaction rate depends on those two things, the number of collisions per unit time. And the number of collisions per unit time is going to depend on the concentration. Concentration is also dependent on pressure and volume. So if you think back to that quick check question, when we halved the volume, that was increasing the concentration. It's also increasing the pressure as well. So number of collisions per unit time is affected by that concentration. It's also affected by surface area. If we grind things up into a powder, suddenly we have more places for those collisions to occur. And lastly, temperature. Okay, it's kind of like speeding things up. I always equate this to little kids. If little kids are walking around the room, they might hit each other, but if you speed them up by increasing the temperature, then they're going to hit each other a lot more frequently. The other part of this is the effectiveness of the collisions. So this is talking about the fraction of collisions that will successfully produce products. Okay, and we can go back to my little analogy with little kids running around the room as well. So if those little kids are running around the room, if they're walking around the room and they bump into each other, probably no one's going to cry. We'll call that a reaction. If they're running around the room and they bang into each other, probably they're going to both fall down and start crying. There's our reaction. So there's the effectiveness of the collisions. The other thing that can affect the effectiveness of the collisions, the other thing that will speed up those collisions and make them more effective, is a catalyst as well. So that's the other one that can affect the effectiveness. So our requirements for effective collisions, this is another graph that you saw yesterday. We're looking at the fraction of molecules, so we're looking at the proportion of molecules at two different temperatures. So in the blue here, I've got the lower temperature. In the red, I've got the higher temperature. You can see that the area under those curves is going to be the same. We're just skewing that higher temperature more to the right. That's why that peak kind of drops down a little bit. It's because it gets spread out further. So when we have collisions between molecules, if they're going to be effective, they have to have sufficient energy to actually break the bonds in the reactants. We call that activation energy. So this is the first thing that we need for an effective collision. So with this graph, you can see that as we raise the temperature, here is kind of the line where I'm going to have an effective collision. So in order for an effective collision to take place, we need a certain amount of kinetic energy. Kinetic energy is the energy of motion. So we need enough speed that those particles are going to hit with enough energy that that's actually going to break the bond. You can see the area under the red curve here is about double what the area under the blue curve is. And as it turns out, for each 10-degree increase in temperature, the reaction rate approximately doubles. There are limitations for that. This is just a general. For room temperature collisions, this is something we can kind of go with an assumption. Okay, the second thing that we are going to need for an effective collision is that we need the geometric shape of a molecule and the collision geometry to match up. So I'm going to put proper collision geometry. So you can see with collision 1, I've got this molecule coming right in. Maybe this is hydrochloric acid with ethene. And it is striking that double bond. And as long as the hydrogen side is facing in, it's going to break that bond and we're going to have an effective collision. If, on the other hand, the chlorine side in collision 2 is facing that double bond, it doesn't matter how hard it hits, it's not going to have an effective collision because we've got the wrong side of the molecule facing in. Same with collision 3 and 4. If they're approaching from the sides, they're not approaching that double bond with the hydrogen molecule perfectly kind of aligned, hydrogen atom of the molecule, they're not going to effectively collide. So that's the second requirement for effective collisions. We've got another quick check here. This is on page 27 of your workbook. So these quick check, you can just pause the video for a second, try and do the quick check questions on your own, and then you can unpause the video and watch the rest of it. Okay, so we're going to go through these quick check questions. It says, which of the factors do you think increase the reaction rate by increasing the number of collisions per unit time? So we said the number of collisions per unit time are affected by concentration, and that concentration is affected by volume and pressure. So if we increase the volume, we're going to decrease the concentration. If we increase the pressure, we're going to increase the concentration. So those are things that are affecting the number of collisions. We also have temperature, because we're going to get more frequent collisions when those molecules are moving faster. And lastly, we have surface area. Now, the second one is the factors that affect the rate by increasing the fraction of successful collisions. There are temperature and catalysts. And the one that affects both of them, you can see we've got temperature on both, so temperature is affecting both. which is why temperature is such one of the easiest conditions to manipulate in our reactions, and that will cause our reactions to go faster. It's also why in industrial chemistry, you almost always find industrial chemistry taking place at fairly high temperatures. Sometimes it has to be a little bit lower to increase yield. We'll talk about that in the next unit, but they're always taking place usually at least 500 degrees Celsius just to increase that reaction rate. Okay, that's me finished talking for today. What I would like you to work in is the activity, 1.3 activity. It's on page 31. I would like you to work in your cohort groups on the whiteboards to try and complete that activity. So it's kind of a little conceptual playing around and trying to figure out what things are affecting our rates of reactions. And then I'd like you to try the questions in the workbook. So read section 1.3 and then complete questions 1, 2, 3, 4, 6, 7, and 8 right at the end of chapter 1.3. I have it on page 33 to 35. Thanks for watching.